Welcome back, students. This is the session 13 from the playlist of electric potential and capacitance, and today the topic for this session is derivation for the energy stored in the capacitor. So here I have written this question, that is, derive the expression for the energy stored in the capacitor when it is fully charged. So this question is important from the point of view of the board examinations, and so let's start doing this question. So we have to find the expression for the energy which is stored in the capacitor when it is fully charged. So for that purpose I have drawn here one simple diagram in which there is a capacitor having a capacitance C, which is connected to an external voltage supply, and here this capacitor will get fully charged by this external voltage source. So let us consider that initially this capacitor is fully discharged, and then it is connected to this external voltage supply, and then it gets fully charged. So we know that the energy which will be stored in the capacitor will be equal to the work done in charging the capacitor. So by using this concept, we will be able to find the energy stored in the capacitor when it is fully charged. Now let us consider that a very small charge, say dq, is transferred on the plates of this capacitor. So the if a very small charge, say dq, is transferred on the plates of this parallel plate capacitor, then the potential difference across this capacitor, that is, say dV, this will be equal to dq upon C, because we know that the capacitance of a capacitor is equal to Q upon V. So if a very small charge, say dq, is transferred on the plates of this parallel plate capacitor, then the potential difference across this capacitor will be equal to, can be written as dV is equal to dq upon C. Now let us consider that at any moment of time, the charge on the capacitor is Q. That is, when I have connected this uncharged capacitor with this external voltage source, then at any moment of time the charge on the capacitor is taken as Q. That is, this is the amount of charge which this capacitor has at any moment of time before it gets fully charged. So if the charge on the capacitor at any moment of time is Q, then the work done in in transferring a very small charge, that is dq, on the plates of this parallel plate capacitor, can be written as, that is dw will be equal to this will be equal to q dv, and this can be written as q dv is equal to dq upon c. So this is the amount of work done in transferring this very small charge dq on the plates of this capacitor. And so in order to find the total work done, what we will do is we will simply integrate this equation, that is dw, integration of dw, this will be equal to the integration of q dq upon c. Now here the limits will be from 0 to, let us say the charge on this capacitor is capital Q when it is fully charged, and here I have taken that this small q is a charge at any moment of time before it is fully charged. Okay? So this capital Q is the amount of charge which is deposited on the plates of this parallel plate capacitor when it is fully charged. So we have charged this capacitor from 0 to Q, and it will be Q dq divided by C. So this will be equal to, now here this the capacitance of this capacitor is a constant value, so this will be taken out, and then I will be integrating this from 0 to Q dq Q, and this will be equal to what? 1 by C. This will be equal to Q square, and the limits is from 0 to Q. So the total work done will be equal to 1 by C Q square minus 0, or the total work done will be equal to, Q square upon 2. This will be equal to Q square upon 2, and so this is equal to Q square upon 2C. See, so the total work done will be equal to 1 by C integration of this Q dq. So the integration of Q dq will be equal to Q square upon 2, and the limits is from 0 to capital Q, where this Q is the total amount of charge which has accumulated on the plates of this capacitor when it is fully charged. So so the total amount of work done in transferring this charge capital Q on the plates of this parallel plate capacitor is equal to Q square upon 2C, and this will be equal to the energy which will be stored in the capacitor. So the energy stored in the capacitor is equal to Q square upon 2C, and this equation can also be written in as, so the energy stored in the capacitor when it is fully charged, this is equal to Q square upon 2C. Now we know that Q is equal to CV, so this can be written as C square V square upon 2C, so this is equal to half CV square. Okay? This can also be written like this, or if you want you can also convert this down. Now here this is Q square, now C is equal to 2 times, now C is equal to Q upon V, so this is equal to Q upon V, so we will be taken in the numerator, so this is equal to 1 upon 2 Q. So the energy stored in the capacitor is equal to Q square upon 2C, and this is also equal to half CV square, and this is also equal to half QV. So thank you very much for joining in this session. In the next session I will be taking up another I will be taking up another question which will be from the topic of the derivation of the means I will be taking up a question which will be where we will be deriving the or we will be finding the equivalent dielectric constant of a capacitor which has got a number of these dielectric materials in between the plates of the capacitor. So thank you very much. Till then, have a nice day. Bye.